What if one of the most durable forms of iron ever used by human beings did not come from a mine, a mountain, or deep geological pressure, but from a foul-smelling peat bog that most people would instinctively avoid stepping into? What if medieval Vikings, so often portrayed as brutal raiders or reckless adventurers, routinely forged iron that resisted corrosion better than much of the steel we depend on today, without electricity, without laboratories, and without any knowledge of atoms or alloys? That iron had a name. It was called bog iron. Today, according to reports by the Federal Highway Administration and corrosion engineering organizations, rust costs the United States approximately $276 billion every single year, more than 3% of national GDP, spent repairing bridges, pipelines, buildings, and infrastructure that slowly fails as metal reacts with air and water. The contradiction is unsettling. Modern industrial society spends hundreds of billions of dollars each year fighting corrosion, while medieval blacksmiths, working with swamp mud, bacteria, and patience, produced iron that quietly endured. This should not be possible, and yet it is true. Most people assume that iron must be taken from the earth by force, that it must be blasted from rock, hauled from deep shafts, and crushed out of stone that has been locked underground for millions of years by geological pressure. That assumption feels natural, because it mirrors the way modern industry operates. But bog iron quietly challenges it at the most basic level. In northern landscapes, shaped by glaciers and wetlands, iron never remained still long enough to become rock. It dissolved naturally into groundwater as ferrous iron, invisible and mobile, moving slowly through soil and fractured bedrock, carried not as a solid resource, but as a trace element suspended in water. Underground, where oxygen was scarce, it stayed dissolved, unseen, and unnoticed. The moment that groundwater rose into a wetland, everything changed. As it reached the surface and encountered oxygen, the iron shifted state. It oxidized, precipitating out of solution as solid particles of iron oxyhydroxide, no longer hidden in water, but physically present in the landscape. Biology completed what chemistry began. Iron oxidizing bacteria accelerated the process, concentrating iron as part of their metabolic cycle. Over years and decades, particle by particle, the metal accumulated inside peat, forming soft, porous nodules and rust-colored crusts. This iron was not finite in the way a mine is finite. If harvested carefully, the same bog could regenerate usable ore within roughly 20 years. One of the only renewable metal ores in human history was forming quietly beneath wet ground, waiting to be recognized. Modern thinking assumes that reliable metallurgy depends on theory, on equations, controlled temperatures, standardized materials, and centralized expertise. We tend to believe that metal only becomes dependable once it is explained. Bog iron production developed without any of those conditions. Across Scandinavia, Finland, Iceland, and wide parts of Eastern Europe, communities with little or no contact with one another arrived at nearly identical ways of turning swamp ore into usable iron. This convergence did not come from shared instruction, but from shared constraints imposed by material and environment. The ore was first roasted to drive off moisture and burn away sulfur that would weaken the metal. It was then smelted in small clay bloomery furnaces, built from local soil, charged with charcoal and crushed ore, and worked slowly over hours rather than minutes. These furnaces never reached temperatures high enough to melt iron. The metal remained solid throughout the process. Instead of flowing as liquid, the iron was reduced chemically. Oxygen was stripped away by carbon monoxide, leaving behind metallic particles that welded together under heat and pressure. What emerged from the furnace was not a pourable metal, but a spongy, glowing mass, dense with trapped slag and voids. No abstract theory guided this work. Only careful observation, repetition across generations, and a clear understanding of limits. The result was not experimental. It was dependable. Modern metallurgy treats phosphorus as a contaminant. Even in small concentrations, it can make steel brittle, especially in cold environments where impact resistance matters most. Entire industrial standards are built around removing it as completely as possible. Bog iron refused to conform to that logic. Naturally rich in phosphorus, bog iron carried that element into the finished metal during smelting. By modern definitions, the resulting iron should have been inferior, unstable, and unsuitable for serious use. Medieval craftsmen discovered the opposite. They did not encounter phosphorus as an abstract number in a specification. They encountered it as behavior. Iron made from bog ore hardened cutting edges more readily than low phosphorus wrought iron, allowing blades to hold an edge longer under use. More importantly, phosphorus changed how the metal interacted with air and moisture. Bog iron resisted atmospheric corrosion far better than iron refined to modern purity. This resistance was not theoretical or measured in laboratories. It was visible to the naked eye. Pattern-welded sword blades relied on this difference. When etched with mild acid, phosphoric iron remained bright while surrounding layers darkened, revealing flowing patterns that only existed because the metals corroded at different rates. What modern industry rejected as a flaw became, in the medieval context, a deliberate and functional advantage. In parts of North America, wrought iron rails forged from bog ore were installed in buildings during the 19th century. They were used to support staircases, balconies, and structural frames in damp coastal environments where corrosion is relentless. Many of those rails remain in place today, still intact, still bearing load, long after their original builders are gone. Modern mild steel tells a different story. Exposed to similar air, moisture, and salt, it often begins corroding within months, unless it is carefully protected. Left untreated, it can lose structural integrity in a fraction of the time its older counterpart endures. This difference is not anecdotal. It is measurable at the microscopic level. Bog iron contains silicate inclusions that form glass-like microstructures within the metal, slowing the movement of moisture and oxygen. Residual phosphorus further alters surface corrosion behavior, changing how rust initiates and spreads. Industrial steel achieved remarkable uniformity and strength. But in refining metal to modern purity, longevity was often sacrificed. The assumption that newer materials must always perform better over long spans of time does not survive contact with the evidence. Vikings are often imagined as impulsive explorers, driven by aggression, bravado, or a reckless appetite for risk. That image survives because it is dramatic. Archaeology, however, tells a quieter and far more disciplined story. When Norse explorers reached the shores of North America, they did not behave like gamblers testing their luck at the edge of the known world. They behaved like planners. Almost immediately, they identified nearby peat bogs, recognized the signs of bog iron, harvested it, smelted it on site, and forged nails needed to repair their ships. Iron was not optional. A single longship required thousands of nails and rivets, forged from hundreds of kilograms of finished iron. To produce that amount, tens of tons of raw bog ore had to be collected, roasted, smelted, and worked by hand. This was labor measured in weeks, not hours. Nothing about this process was improvised. It reflected generations of accumulated experience carried across the North Atlantic. Viking expansion depended less on daring than on a clear understanding of what could not be replaced once it failed. By the time Vikings crossed the Atlantic, bog iron smelting was no longer a rare or specialized craft. It was widespread cultural knowledge, practiced across farms, seasonal sites, and small communities, rather than controlled by a narrow elite. Archaeological analysis of slag tells this story clearly. The waste material left behind shows inefficiencies that would frustrate a modern engineer. Large amounts of iron remained trapped in the slag, and furnaces were often rebuilt rather than optimized. Yet the iron that emerged was sufficient for tools, fasteners, and repairs. This was not guarded expertise passed down through formal instruction. It was embedded in the landscape itself. People learned to read the signs. Certain plants thrived where iron-rich water surfaced. Standing pools carried iridescent films that shattered when touched. Rust-colored stains marked moving water. Knowledge moved through observation, repetition, and shared labor rather than manuals or formulas. Because it was decentralized, the system was resilient. Anyone with patience, attention, and time could participate, and no single failure could erase the skill. Bog iron was not abandoned because it failed to perform. It was abandoned because blast furnaces scaled faster than landscapes could regenerate. With the introduction of coke-fired furnaces, iron production shifted from kilograms per day to tons per day. Metal could now be melted completely, poured into molds, standardized, transported over long distances, and sold as a predictable commodity. The economic advantage was overwhelming, but that scale came with trade-offs. In refining iron to achieve uniformity, industry removed elements that had once provided natural protection. Phosphorus was treated as a defect to be eliminated. Silicate inclusions were refined away in pursuit of consistency. The result was iron and steel that behaved differently in the open air. Without those natural features, metal rusted readily and required constant intervention. Paint, coatings, galvanization, and complex protection systems became necessary simply to preserve what earlier iron achieved on its own. The paradox cannot be avoided. We did not eliminate corrosion. We multiplied it, then built entire industries to manage the consequences. Today, corrosion costs the United States $276 billion every single year. Globally, the cost exceeds $2 trillion annually, draining resources through failed bridges, ruptured water mains, weakened pipelines, and reinforced concrete that crumbles silently from the inside out. This is not the price of neglect. It is the price of design. We produce steel that rusts easily, then spend enormous resources coating it, galvanizing it, painting it, and electrically protecting it, just to slow a process we have already set in motion. Entire industries exist to manage corrosion rather than prevent it at the source. We apply layers of protection to metal that no longer protects itself. In removing phosphorus and silicates to achieve uniformity and speed, we engineered durability out of the material itself. The problem did not disappear. It expanded. Bog iron was slow. It was limited in quantity and demanded physical labor. It was never suited to mass production or global supply chains, but it endured. 1,000 years ago, a Norse blacksmith stepped onto a distant shore at the edge of the known world. His ship needed nails. Without mines, factories, or supply lines, he turned to the landscape itself. He found a peat bog, recognized the subtle signs of bog iron, shaped a furnace from clay, burned charcoal from local wood, and forged the metal he required with his own hands. Those nails survived a millennium buried in wet, acidic soil. They endured conditions that destroy many modern fasteners in decades. That survival was not accidental. It was the result of choices made slowly, with an understanding of limits rather than an attempt to overcome them. This is not a failure of intelligence or progress. It is a reflection of priorities. Modern society values speed, scale, and uniformity. The Vikings valued sufficiency. They did not endure because they were stronger or wiser than we are. They endured because they worked within constraints they understood and accepted. History does not last because it is efficient. It lasts because it is enough. If this story echoes something in your own family's past, a memory of migration, settlement, labor, or adaptation carried quietly across generations, that memory matters. History survives not because it is written down, but because it is remembered, long after the tools themselves have rusted away.